combination reactions? Because we kind of whipped through balancing those out, doing some predictions on those. I'm going to take that as a no. We'll move into our decomposition. So our general form for our decomposition. We start with a species. We do something to it, which usually involves heat, okay? Which we could see as what kind of symbol?
Delta.
We'd see the delta show up above our reaction arrow. And then that would then turn into 2 or more species. Okay, so it breaks it apart. You are doing a decomposition lab in a couple weeks. Okay, it's kind of a boring one. You're taking salt that has water in it as a solid, and then you heat it up. What happens to water when you heat it up? It turns into a gas. And so what you started with was a salt with water locked together, and you end with the salt and water as a gas. So you've decomposed it. Okay, you've changed the phase. There are other versions of decomposition reactions that tend to be a little bit more spectacular, like not this one, but some of them tend to be a little bit more spectacular than others. So let's take a look at this one. We're going to heat solid mercury to oxide, and it's going to produce mercury metal and oxygen gas. So we want to now take our swing at trying to convert this into an actual equation. So we'd start with mercury to oxide, which is interesting. That's, what is that, our third and fourth word in? Yeah. So mercury, symbol for mercury is? Hg. Our symbol for oxide? I do not accept that. It is just O. What is the name of O2?
Oxygen gas.
Oxygen gas. Okay. If we need 2 oxygens to balance it, that could be a separate issue. Okay. At this point, all we're doing is dropping the symbols. We aren't specifying how much of each of those individual elements need to be there. Okay. How do we decide how much needs to be there? We need to know the charges. What is the charge on mercury? How do you know it's +2? Says it in the name. That's what the Roman numerals meant. Oxide? -2. Is our formula balance?
Yeah.
Yes. We don't need to bring in any superscripts or subscripts. Okay. What else would we now add? No arrow. Not yet. We need to specify the phase. It's a solid. Now we can add our arrow, which is our produces, but we won't add just the arrow. We're going to put the delta because it said heating. Right? What does this produce? Hg. Since it's a metal, we could go through and say solid, except we look at the periodic table and we think back to that first unit when we talked about properties of periodic or our elements. And we will not be writing a solid, we will be writing liquid. Mercury is a liquid at standard temperatures. Okay. Plus O2. Why does the 2 come into play? It's oxygen gas. Oxygen is a diatomic element. We need that second oxygen there. And it is a gas. Okay. Questions about anything written up there? Okay. Before we say this is done, Sam brought up an interesting point. It's not balanced, so we need to balance the equation. How do we balance it?
Find out how much we have.
Same amount on both sides.
How much mercury is on the left? Mercury on the right. Mercury's balanced. I don't know what you're talking about, Sam.
You got 2.
Oh, okay. Oxygen. How many oxygens are on the left?
1,
How many oxygens on the right?
2.
Not balanced. What do we need to do?
Add coefficient.
Put a 2. Okay, so we put a 2 and it's balanced, right?
No.
Okay. It has to be a coefficient. We cannot change the formula. Okay, so it needs to go out front. As soon as we start balancing our equation, we have to change the coefficients. Which then means our oxygen is now 2. Is oxygen balanced?
Yes.
Yes, we've changed the coefficient, so you must go back and check, because as he's just now pointed out, our mercury has now become 2 on the left, which then means we need 2 on the right. We'll do that by putting a 2 in front of the mercury there. How many oxygens? 2 and 2. We changed the coefficient, so again, annoyingly, we have to go back and check and verify that everything's now balanced out and we're good to run. Questions about that? Okay. Your turn.
I got questions.
Wait, about the your turn? No? Okay. So, our general form, a metal hydrogen carbonate. So this is, again, something that we could theoretically predict. So I'm giving you some information to help you predict this. You will not be expected to predict decompositions or combinations on the exam. A metal hydrogen carbonate will decompose to give a metal carbonate, water, and carbon dioxide. Okay, so we're given the general information of what happens with this type of decomposition. Okay. So what does sodium hydrogen carbonate decompose into? So what are our products? 2 of them should be immediately obvious and easy. H2O and CO2, because that's water and carbon dioxide. It has nothing to do with anything else. Those are simple right out of the gate. Those are a complete compound. What's the third product?
Na.
Okay. Na, you're saying sodium. Does it say we're going to form our metal hydrogen carbonate decomposes to give just a metal, water, and carbon dioxide? Is that what it says?
Metal carbon.
A metal carbonate. So not just sodium by itself, but sodium with
Carbon.
carbonate. What's our formula for carbonate? CO3. So now let's go through and put it all together. Sodium hydrogen carbonate decomposes. So our formula becomes NaHCO3. Okay, we got to make sure that that's actually correct. What's the charge on sodium?
1.
A +1. Charge on our hydrogen carbonate? Hydrogen carbonate is a -1. I heard a variety of answers in there. I heard a +1, which I have a feeling you were referencing the hydrogen. And I heard a -2, which I have a feeling you were referencing the carbonate. Hydrogen carbonate is the combination of those two, which gets us to a -1. Is our formula correct? Yes. Sodium hydrogen carbonate decomposes, so there's our reaction arrow, into our metal carbonate. What was our metal in this case? Sodium. Our formula for carbonate? CO3, not HCO3. HCO3 is hydrogen carbonate. This is just carbonate. Plus H2O plus CO2. Okay. Officially, we should go through and deal with phases. Did I specify any phases in there to help you figure that out? No, so I wouldn't expect you to know these, okay, or predict any of those. I kind of have a vague recollection that you should be able to figure out the phases on the last 2 species. What is the phase of CO2?
Gas.
It's a gas. The phase on water? Liquid. Okay. Again, I don't expect you to know that, but you should. Okay. The other 2 don't stress on the phases for. Should we go through and try and balance the equation yet?
No,
Why not?
because with the sodium carbonate, you don't know how many you have yet. Like how many, sorry, like that part isn't balanced yet.
We have to make sure our formula is correct. Do we have the correct formula for sodium carbonate? As an ionic compound, we should be able to predict that formula. We predict that formula because the product we're making has what charge? A balanced charge, which is 0 or neutral. What is the charge on sodium? +1. Charge on carbonate? -2. Is our formula correct for sodium carbonate? No. What do we need to make that correct? I need 2 sodiums. So I just need to put a 2 out front, right? Because that's what we've been doing. We only put a 2 in front if we're balancing the equation. We're not balancing the equation, we're balancing the formula. Where do we put our 2 for the formula? As a subscript immediately after the element we're trying to reference, in this case the sodium. Now that we have the correct formulas, now we can balance the equation. To balance the equation, what do we start with? How many sodiums on the left? Right? 2. Remember we have that subscript, which then means I need a 2 in front of the sodium on the left. I'm going to do that in black ink. Sorry. So our sodiums are balanced. What should I try and balance now? Okay, hydrogen. How many hydrogens on the left? 2. Why is it 2, not 1? The 2 applies to everything afterwards. That's supposed to be a bunch of arrows. How many hydrogens on the right? 2. So hydrogen's balanced. Should I try and balance carbonate? But carbonate shows up as a product, doesn't it? We have to realize that that carbon from CO2 had to come from carbonate. Okay, so we cannot balance carbonate across this equation. We will unfortunately have to break it down into the individual elements. How many carbons on the left? Carbons on the right? 2, because there's 1 here, and there's 1 here. Everybody got that? Now we can look at our oxygens, and I've run out of space, so I'll just put it on the side. Oxygens on the left. 6. There's 3 from the carbonate, but there's 2 carbonates there. So I got 6, and on the right I have 6, showing up in 3 different locations. Okay? So we now have our correct balanced equation. So real quickly, let's throw down a sum of the coefficients with multiple choice answers being 2, 3, 5. Anybody creative? 4. E, pine nut. What's the answer? Our answer becomes C. We're adding 2 plus the implied 1 plus the implied 1 plus the implied 1, which gets us up to 5. Our answer is C. Make sense? Okay. So let's try another one. Another rule set. See what you can come up with. Answer is 3. Okay. So let's go through and work that out. What is calcium carbonate? What's the charge? There's the word. The charge on calcium. Charge on carbonate. Is that formula balanced? Yes. Did I give you any phase information? So should you worry about it? Good. Produces what? It says metal oxide is one product, and the other product is CO2. I got really original there. Okay. So a metal oxide, what was the metal in calcium carbonate? Calcium. What does oxide mean? Oxygen. The other product? CO2. What is the charge on calcium? Positive 2. Charge on oxygen? Negative 2. Is our formula correct? Yep. CO2 is already given to us. We don't have to predict any of that. That just comes straight out of the name. So we could check our equation. How many calciums? 1 on each side. How many carbons? Carbons is 1 on each side. Oxygen, it's okay. 3 on each side. It's balanced. Sum of the coefficients? 3, because there's 1 in front of each of those 3 symbols. We all good with that? Balancing is too easy, right?
I'm not saying yes,
So let's make it more challenging. Single replacement reactions. Okay, so we're going to bring in some extra terms that come into this. Those of you in the Tuesday lab will remember some of these. We'll refer to our metals as active. Okay? Our more active metal will displace another metal in a compound. Okay? The added caveat or the added issue with our single replacement reactions is you are required to be able to predict the products of the reaction and then actually say, should that reaction have occurred? Which is a challenging aspect. So two big pieces come out of this. That's a good formula to start with, considering that that's the name written there. So let's make some adjustments. Just erase that. Okay, let's come up with a potential equation for this. So iron solid gives us what symbol?
Fe.
Fe is iron, I agree. Said iron solid. Phase solid is mixed with plus aqueous copper 2 sulfate, symbol for copper. Cu, symbol for sulfate. Fine, just laugh at me and not tell me what the answer was. SO4. Do we know the phase? We know it is aqueous. Okay. Since we have a compound, let's make sure that the compound or the formula we wrote is correct. What's the charge on copper? Copper is a +2. How do we know it's a +2? Given to us in the equation as a +2. Sulfate is what charge? A -2. How do we know sulfate's a -2? It's one you got to have memorized. Is our formula balanced? Yes. Okay. So we now want to go through to predict our products, and I wrote way too big, so I'm going to end up erasing everything. Try that again real quickly. That's why I had to erase that real quick. To produce. What does it produce? So if we're following our general equation format, our metals, which we said were blue, need to exchange locations. So our metals would be the iron and the copper. So we need to exchange their locations. So I end up with copper with what phase? Interestingly enough, solid plus Fe SO4. Here's where we can potentially run into some issues here. We now have to make sure our formulas are correct, and this is actually why that other equation showed up. What is the charge on sulfate?
-2.
-2. What is the charge on iron?
We don't know.
You don't know. Okay, by having to predict this, we don't have any information that allows us to decide what the charge is on that iron. Okay? For the sake of simplicity, we will make an assumption. What will that assumption be? It will also be +2. Okay? In an exam situation, if you run into this and you're questioning it, raise your hand. I'll come up and check and be like, oh, yeah, you're right. I should have told you that. Here's the information. Or it'll be a species that you are required to know the charge on. For instance, like the formula that I already quickly erased. Okay? So let's take a look at our equation. Is everything balanced? Yeah, so this is one of the nice things about assuming the charge comes out the same, is that we can now have our balanced equation. We've now done a single replacement reaction. So the next question becomes, should a reaction have occurred? Right. And that's a much harder question to ask. Okay. That goes back to the more active metal. The more active the metal, the more likely it wants to be in a compound. So if we look at this, reactants versus products, let's say the reaction did occur. Okay. When we then look at our solution after we've mixed them, what would we expect to find within it? If the reaction did occur. Do we expect to find iron solid or copper solid? Copper solid, that's our product. So if it did occur, this is what we would expect to see. Is that how you spell occur?
Yeah.
Good. I didn't want to write out happen. Okay. Which metal is with a compound? Iron. Which is the more active metal? Iron. That's if the reaction did occur. What if the reaction did not occur? What would we expect to find when we looked at the solution? We would see the iron solid. This would be our did not occur. Okay. So if it did not if it did not occur, what's our most active metal? Copper. If it did occur, what was our most active metal? Iron. Okay, well, which one's more active?
Whichever one occurs.
Depends on what happened. We'd have to go to an experiment and test it. You're right. Okay? It has to be experimentally determined, okay, at least at this stage. So we'd have to look up some tables to find out. Okay? Or what you do in lab is you're building your own tables of deciding which one was more or less active. By evaluating, looking at the experiment and saying a reaction occurred, that means the products of my single replacement reaction, whichever one is in the ion form or in a compound, is the more active metal. Okay? Kind of makes sense? At least those of you in Tuesday can say yes or no.
Yeah.
Thursday can still be confused. Okay? So, let's look at a new reaction that we should be able to fully be able to predict. We've got it listed here. Go ahead and balance that out. Tell me what you get. That one, absolutely, you should be able to predict with no questions asked. You can still ask questions, but.
Like
First product, lead, solid. Okay. Plus zinc with sulfate, and theoretically it would be aqueous. By predicting our products, we have to make sure that our products are correct. Well, lead all by itself is a solid. That's fine. What about the zinc? Did we do the zinc sulfate correctly? What is the charge on sulfate? How do you know that? You're supposed to know it. What is the charge on zinc?
we don't know.
Yes, you do. It's a positive 2. You're required to know that. Okay. This is a case, this is one of the 3 that I told you have to have memorized, unfortunately, outside of our columns. Okay. So you are required to know zinc is a +2, which then means you know your equation is correct and balanced. So now what we want to do is decide, should this reaction occur? Well, this is going to come down to which metal is more active, zinc or lead. Okay. So we can go into an experiment and test it, or what we can do is look at an activity series. Okay. The activity series, depending on frame of reference, will sometimes show increasing activity or decreasing activity. Make sure you know what it's trying to show. In this case, decreasing, which means at the top we have the most active, and at the bottom we have least active. Okay? So to do this interpretation, we now need to look for the 2 metals that are relevant. Okay? I don't care about lithium, potassium, or calcium because they're not in the equation, so ignore them. What we need to focus on is zinc and, where is it? And lead. Which one is more active? Zinc. It's higher up on our activity series, and since we said the highest up was our most active, zinc wants to be in a compound or in its ionic state, its charged state. So now look at our equation. Where is zinc in a compound? On the reactant side or the product side? It's on the product side, which means this reaction does actually occur. Okay. One of the extra issues that pops up within the lab, you'll notice that when we look at this, we've got everything nicely balanced. We can see all of those charges. Everything's neutral. Everything looks pretty. When you move into lab, it doesn't quite look so nice, and it looks something more along these lines. We think back to the rule set that we just talked about. I said the more active metal needs to be in a compound. If we look at that equation that's drawn down there in purple, which element is in a compound? Really hard to tell because we're showing all the ions. We don't actually see them in a compound. Okay. Most aqueous compounds, which we'll have to discuss it in lecture because I don't know you'll see it in lab, will completely dissociate into their ions when they hit water. This is why when we dissolve sodium chloride in water, we said that was a chemical response because we're breaking the bonds. Okay? So we're looking at the ions here to help us determine this. So if we're in the ionic state, what we then need to go for is, instead of looking for the metal in a compound, look for the metal as solid. An ion. Okay. The more active metal displaces another metal. Oh yeah, that rule, I can't just erase that. That's not nice. So let's just say more active down here is in the compound or is written as an ion. For the lecture, you'll probably see it in the compound. For the lab, for some reason, they decided to show it in the ionic form. So if we go back to our equation in purple, zinc being our more active metal, because it's higher in our activity series, needs to be shown either as in a compound or in an ion. If we don't see compounds, we need to find zinc as an ion. Where's zinc written as an ion? Interesting. In the exact same location as if it was with a compound. Okay. That's our interpretation of it. In our single replacements, we are starting with something with no charge, and it becomes charged through the course of the reaction. The species that was charged, what happens to it? Lead started charged, and it became not charged. Okay? So we are changing the charge, which we're going to refine in a little bit, through the course of a single replacement reaction. Okay? Which is actually much trickier than just looking at the charges balancing around. Okay? Can we actually use this to something a little bit more helpful? Let's take a look at some extremes. Gold is our least active metal. Where have we seen gold before? In money. Why would we choose gold as our standard for currency? It doesn't react with anything. Okay? That's why we have gold as our currency. Okay, that, and it's a little bit more abundant than platinum. Okay? What happens if instead we'd use lithium? Go to Fort Knox, right? Fort Knox, collect all your gold reserves. Everything's sitting in there. Okay? And that's the big thing. They got all that security to protect the gold so nobody gets in and steals it, or anything like that. Let's say it was lithium. Now what does the terrorists do?
Just make lithium.
They break in with water bottles. What happens when you hit water on lithium? It reacts and becomes an ion, which dissolves in water, and it now floods and goes down the drain. There went all of your wealth.
But now it's just spread through the common,
For the sewer people.
Yeah, to the sewer people. So we're picking, excuse me, gold as our currency because of its chemistry. It doesn't have any chemistry. Where else do we use gold? Jewelry. What if we picked a different metal that reacts with our skin instead of gold?
Oh, that'd be awesome.
Yeah, wouldn't that be awesome? If you buy really cheap silver, what happens?
We don't have green necks, green ears, green
Okay,
hands.
we start dyeing our skin because the metal is decomposing and staining our skin. It's why one of the reasons why we use gold for jewelry, because it doesn't stain our skin. Okay? So gold is very inactive. Okay? That can help you locate and reference your activities on these, and it gives you some idea of their reactivity. The less active the metal, the more it wants to stay all by itself, okay, with its neutral state. Okay? Questions about any of that? Or maybe like a quiz where you were asked to predict reactions and decide, did a reaction occur? Well, how did we decide if a reaction occurred? We had to do the experiment, or we looked at an activity series where somebody actually already did the experiment and told us the result. Okay? So how can you predict if you can't go into the lab to test it? You'd have to know the activity series. So you could go through and memorize that. I think memorization is a big waste of time. I will give you an activity series. Okay? So if you take a look at your exam, I think all of them have the same version. Even if you look at exam 1 and exam 2, the cover page, it lists an activity series. You now have the context of why that was there. Okay? It may not be the same for your exam, because I can go through and change and put different metals on there and switch it up. Why would I switch up to different metals? Because I'm changing the question. That's why. Okay? That's it. You'll notice also that in the activity series, for any one of these questions, you have to compare how many metals? 2. But when we look at the activity series, you'll always see more than 2. Why more than 2?
You never know what metals are going to be.
We don't know what metals are there, and if I only give you 2, it's too easy. So I'll give you 3 or 4, okay, just to make it confusing. Okay? So I might pick magnesium and manganese. Yeah. So back when I told you to memorize the elements and you needed to know their symbols and all that?
You really meant that?
Yeah. Okay. Along those lines, I did also really mean, like,